Okay, we're going to talk about binary trees. Binary trees are a way that a set can be implemented. There are many ways that sets can be implemented. Um, you could use an array, you could use a binary tree, you could use various different variations of binary tree-like things. Binary trees are fairly easy to understand, so we're going to use that. Um, and remember, the property of a set is that you can't have duplicates. So if we were to grab some numbers, 1, 5, 2, 3, 7, 99, and 0. Actually, let's not start with 1. 6. And we wanted to store all of those in a easy to access, or quick way to access structure. A binary tree is a good idea. So we arbitrarily take the first one, 6, and we make it the root. Right? It's a node. It looks very similar to a linked list. It has a next and a previous, but we call it left and right. And they start off just pointing at null. Then we go to put in 1. 1 is smaller than 6, so it goes over here, 1. And it also has left and right. Then we're going to go put in 5. 5 is smaller than 6, greater than 1, so we'll put it over here, 5. Then we got to go to put in 2. 2 is less than 6, greater than 1, less than 5, so 2 winds up here. 3, less than 6, greater than 1, less than 5, greater than 2. 3. 7 is greater than 6, so it's going to go over here. 99, greater than 6, greater than 7. And 0, less than 6, less than 1, winds up here. And anywhere where it's not pointing at anything, it would be pointing at null. I'm just going to draw it, it would take too much time. So now, if we wanted to see if the number 7 is in here, we just look at 6 and say, well, it's not 6, so and it's greater, so it's going to go here. And that 7, we found it. If we're going to look up 4, 4 is less than 6, greater than 1, less than 5, greater than 2, greater than 3, no, not there. So 4 isn't there. So as you can see, we can't store duplicates because 6 is already there. So we could overwrite it or whatever, but we can't have two 6s. There's no concept of is 6 less than or greater than 6. It doesn't make any sense. It's quick to access as well, right? As I said, there's various structures we could use. Some of them wind up being all the same depth. This one, worst case scenario, if you were to put in numeric order, 0, 1, 2, 3, 5, 6, 7, 99, you'd wind up with something like this. Right? And all of these would point to null. Which looks suspiciously exactly like a linked list. So worst case, that's what this is. But like I said, there's other structures that are different tree structures that are able to rebalance that would wind up making it look more like something like this. Right? Where everything's at the same level, so you'd only have to go down at most search down 4, for example. Right? So as this grows, it gets longer to search, but generally speaking, it's not very long. Right? So that's one way we could implement a set. There's another way using arrays. And it doesn't matter how a set is implemented in whatever language you're using. It's a structure that's probably optimized and probably heavily optimized to be fast. So if we're using an array, I'm going to not do what you should do. I'm going to make our lives simple. And I'm just going to make an array with 10 entries. 10 entries because the math that we're going to do becomes simple. So let's say we wanted to put in some words like hello or evil. Oh, actually, I'm drawing this too close. I'm used to a much bigger whiteboard. Um, hello, evil, world, I like soup. Now, remember that Java has certain standard methods like the equals and the hash code. There's some rules around that. If you override equals or hash code, you have to override the other one. We're not going to worry about that right now. We're using strings. They do that. They follow that rule. So hash code is just something that takes an object and converts it to an int. There's some particular formula for strings. It's well defined. It's a lot of math. It is irrelevant for this. I'm just going to arbitrarily pick some numbers. Okay? So let's say that the hash codes spit these out. Again, totally random. I have no idea. So we're going to take each of these and we need to make them fit into this array. So how do we take the number 872 and make it between 0 and 9? Well, that's why I picked 10. So 872, we just mod each one of them by 10. What does mod do? Pause, think about it. Right? So mod gives us the leftover of the division. So 872 divided by 10, it'll have a leftover of 2, right? Goes in, do the math, right? So this one winds up being 2, this one winds up being 7. So we just have to grab the last digit. Right? So 276264. So that 2 means we go to this array here, and now we can use a linked list or an array list, doesn't matter, and we can put in hello. Evil is going to go into 7. World is going to go into 6. I is going to go into 2. 2 already has hello in it, but that's why we're using a list. We can add another one. Same with 6 for like. And soup goes into 4. So now, and if we just kind of kept going with this, say we added millions of items, say we added 10 million items. And let's say that last digit's nice and randomly distributed. There's a, whatever in there. What is the average size of one of these chains going to be, one of these lists? Pause, think about it. Right? So it's a million divided by 10. Each should be about 100,000. So it's 100,000 lists, or lists of 100,000 items. And 100,000 items can take a long time to search through it. However, bonus thing, 100,000 is way less than a million. So it's 10 times less searching to go through, in essence. So what you do is if we want to find soup, or actually let's go with like. So we want to find like. We get the hash code, 814. We mod it by 10, which gives us 4. So we're going to go to array entry 4. Oh, sorry, that was 82, my mistake. 82 mod by 10, that's going to give us 2. So we go to array index 2, and we look at hello, and we get the hash code for hello, which is 872, which is suspiciously not 82. So we move on. We get the hash code for, did I do? Sorry, I screwed up twice. Wow. It's 916. That's when I wish I could go back and edit my video. 916, which gives us 6. So we're in 6. We look at world. We hash world. It's 396, which is not 916. We move to the next one. Now that's a way we could do it. I'll show you another way after. We hash to 916 for like. Like is also 916. That does not mean they're the same. think about it. An int holds about 4 billion values. You can have more than 4 billion strings. Therefore, eventually, two strings must have the same hash code value. Um, so that's what we would call a collision on that. Um, Two kinetic collisions. One is this collision of six, right? They both hash to six. That's a collision. But then there's another collision of everything that has the same hash code. You can't just look at the hash code and say, are these the same thing? This is why we also have to have the equals method. So we don't actually probably wouldn't compare the hash codes at all. What we do is we use a hash code to get to this index, and then we'd call the equals method and say, is world equal to like? No, it's not. Is like equal to like? Yes, it is. All right, we got it. Um, if we were looking for foo instead, which has a hash code of 222, right? We're going to come into, we're going to mod it by 10. We're going to get it 2. We're going to compare hello to foo, not the same thing. We're going to compare I to foo, not the same thing. We're at the end, it's null. So then foo wasn't present, right? So it's a quick way to look things up. That's, sorry, it's not a quick way to look things up. It's a quick way to understand if something is present in a hash, in a set or not. Or to add it into the set. So both this or the binary tree work well. You would probably never actually implement it in either way that I've shown you. That doesn't matter. It's the concepts we're going for. So the whole idea of a set is to very easily be able to, sorry, I'm being attacked by a cat. Being very easily and quickly being able to find out if something's in the set or not, and add it to the set or get it from the set. And that tree structure or this, paring down the lists allows you to do that. Now, in reality, this array is going to be much. I'm seriously getting attacked by a cat. It's going to be this array is going to be much larger. And again, you wouldn't implement it this way. But if you were to do it this way, you'd have a much larger array. These chains would be much shorter. So that is how a set could be implemented. You do not need to worry about the actual implementation of a set. If you're using Python, it's fast. If you're using Java, it's fast. If you're doing C++, it's fast. They do whatever they need to do to make those things fast. This structure also gets used in maps, and there'll be a video on maps coming up as well.